In this lesson, we're going to be graphing square root functions, comparing square root functions using average rates of change, and solving real-life problems involving square root functions. Graphing square root functions. A square root function is a function that contains a square root with the independent variable in the radicand. The parent function for the family of square root functions is f of x equals the square root of x. The domain of f is x is greater than or equal to 0, and the range of f is y is greater than or equal to 0. The value of the radicand in a square root function cannot be negative, so the domain of a square root function includes the x values for which the radicand is greater than or equal to 0. And notice the radicand is just the inside of the radical here. And it makes sense because if I try to take the square root of a negative number, I'm not going to get any real number that pops out of that. For example 1, we're going to describe the domain of f of x equals 3 times the square root of x minus 5. Well, what I'm going to do here is look inside of the radical, the radicand, and I have x minus 5. Well, I know that I can't have anything that's negative inside the radical, so I want x minus 5 to be larger than 0, or at least 0, so it can't be negative. So what I'm going to do is I'm going to set x minus 5 greater than or equal to 0, because this has to be larger than or equal to 0 in order for me to actually get a real number that pops out of this. So to solve this, I'm just going to add 5 on both sides, and I get x is greater than or equal to 5. So this is my domain. So my domain is x is greater than or equal to 5. And now we're done with this one. For example 2, we're going to graph the square root function. F of x equals the square root of x and then plus 3. And then we're going to describe the range of the function. Well, what I say to my students is whenever we're graphing and feeling unable, we can make a table. So I'm going to make a table of values. So I have x and then f of x. And I want to be very particular in which x values that I'm picking. Okay, so the x values I pick, I want to make it easy for me to be able to plot the points. So what I want to do is I want to pick perfect square x values that make whatever is going to pop out of the square root a number that's easy to manage. So I'm going to start with the first perfect square, which is 0. So I have 0, and then I'm going to do 1. And then from 0 to 1, the next perfect square is 4. So I'm going to do 4. And then I'm going to do 9, because that's 3 squared, and then 16. And I noticed that for my graph, 16 is how high the graph goes for the x, so I'm going to stop there. But you could go 25, and then 36, and so on. Anyway, now I'm going to plug these in to my function, and then get my output values for f of x. Well, the square root of 0 is 0, and then plus 3 is 3. And then here, the square root of 1 is 1, plus 3 is 4. The square root of 4 is 2, plus 3 is 5. The square root of 9 is 3, plus 3 is 6, and you can kind of see the pattern here. Because I chose these perfect squares, that just means I'm going to be increasing my output by 1 each time. So you can take a guess, this is going to be 7. And if I actually try that, I do the square root of 16 is 4, and then plus 3 is 7. So I'm just going to plot these points. I have 0, 3, and then 1, 4, and then I have 4, 5, and then 9, 6, so 9 would be right here. And then I have 16, 7. So I'm going to sketch a curve through this. And notice I only have an arrow going this way. I'll draw a better arrow here. But I only have an arrow going this way because the domain of this function stops here. Okay? To the left of 0, there's no number I can plug in that'll give me a real solution. So that's going to help me figure out my domain, but that's not even what they're asking here. They're asking for the range. And notice the lowest range value is 3. I can't get a number that's below 3 that's going to pop out of this function. So my range is going to be y is greater than or equal to 3. And now we're done with this one. So now we're going to talk about radical functions. A radical function is a function that contains a radical expression with the independent variable in the radicand. A square root function is a type of radical function. You can transform graphs of radical functions in the same way you transform graphs in functions previously. In example 2, notice the graph of f is a vertical translation of the graph of the parent square root function. So if I scroll down here, we notice that all of our function transformations for previous functions, like absolute value functions, linear functions, exponential functions, and quadratic functions behave the same way as radical functions. So if anything is happening on the inside, that's going to be a horizontal change. And if anything's happening on the outside, that's going to be a vertical change. And remember, for the horizontal changes on the inside of the function, and in this case that means the inside of the radical or the radicand, that is going to be reversed. And then the stuff on the outside is just going to be the same thing. So what I mean by that is the horizontal translation to the right, it's going to be minus h, and then a horizontal translation to the left is going to be something plus h. And then on the outside of the function for a vertical translation, adding k is going to be a translation up, subtracting k is going to be a translation down. And then the reflections, remember that's just when we make it negative. So a reflection that has a horizontal change is going to be in the y-axis, because I'm flipping over the y-axis, that's acting as my mirror. That's going to be when the negative's on the inside. And then for a vertical change, that's going to be on the outside. That's going to be when I'm flipping over the x-axis. And then stretches and shrinks, horizontal stretches and shrinks are going to be on the inside of the function, in this case the radical. So here I have the 3 times x inside, and then I have the 1/2 times x on the inside. And then a vertical stretch or shrink is going to be, the multiplier is going to be on the outside. So here I have the 4 on the outside, and here I have the 1/5 on the outside. And remember, all of the stuff on the inside is reversed. So the smaller scale factor on the inside is going to be a stretch, and the larger scale factor on the inside is going to be a shrink, whereas the larger scale factor on the outside is going to be a stretch, and the smaller one on the outside is going to be a shrink. For example 3, we're going to graph g of x equals negative square root of the quantity x minus 2, and then compare that graph to the parent function, which is f of x equals the square root of x. Well, first I'm going to make a table. And once again, I want to deal with easy numbers that will get me something that is easy to graph, that I can plot on my graph. So I want to make this a perfect square. Well, the first perfect square is 0, but in order to make the inside of this square root a perfect square of 0, I need to make x equal to 2, because 2 minus 2 equals 0. So my first x value I'm going to plot is 2. And then the next one is 1. So to get that perfect square equal to 1, I'm going to plug in 3 here, because 3 minus 2 is 1. So if I plug in 3, that will get me something. And I should honestly just do these out right now. So the square root of 0, because if I plug in 2 here, I get square root of 0, and then make that negative, that's still 0. And then for 3, I get this 3 minus 2 is 1. The square root of 1 is 1, and then make that negative, that's negative 1. And then the next perfect square after 1 is going to be 4. So the number that makes this equal to 4 is going to be 6. So if I do 6 minus 2, so 6 minus 2, that's 4. The square root of 4 is 2. Make that negative, negative 2. And then the next perfect square after 4 is 9. And that doesn't fit on our graph. So I'm just going to stop here. But you could, in theory, extend this table. Anyway, I picked my x values that gave me perfect squares, so I could take them and then plot them. But let's plot these points now. So I'll plot the point 2, 0. So that's right here. And then 3, negative 1. And then 6, negative 2. And then you can kind of see where the function is going. So I'll sketch that out. And remember, I'm only drawing my arrow going to the right because the domain of this function stops here. Now we're going to compare this to the graph of f of x equals the square root of x. Now you could graph this, but you can also just tell what's happening. Okay, I have a minus 2 on the inside. Well, that's a translation 2 units right. Okay, and then I have this negative on the outside. Well, that's a reflection. So what I can do is I can say that I have a reflection in the x-axis, and then I have a translation 2 units right, because after I reflected it with the negative sign, I'm moving this 2 units right. So translation 2 units right. So I've graphed this function successfully, and then I've described the transformations from the parent function, and now we're done. To graph a square root function of the form y equals a times the square root of x minus h all plus k, where a does not equal 0, start at h comma k. So let g of x equal negative 2 times the square root of x minus 3 all minus 2. Part A, describe the transformations from the graph of f of x equals the square root of x to the graph of g. Part B, graph g. Well, you can figure out what the transformations are without even graphing it if I just look at this, okay? So the first thing that I would recommend doing is dealing with the a value. So this a value is telling us a lot. This negative sign means that I have a reflection in the x-axis because remember, this is on the outside of my function. Outside is a vertical change, and going from up to down, that is a vertical change. So this means I have a reflection in the x-axis, so I'm going to write that down. But that's not the only thing that this a value of -2 is telling us. The 2 part of this is telling me that I have a vertical stretch with a scale factor of 2. Okay, and now I'm going to deal with my translation. Well, this -3 on the inside means that I'm translating 3 units to the right, and then the -2 on the outside means I'm translating 2 units down. So translation, 3 units right, and 2 units down. So I was able to figure this out with just looking at the function without even graphing. But now I'm going to graph it. So I'm going to make my table of values. X and then g of x. And remember, whenever we're doing the square root functions, we're going to pick values that give us perfect squares. So the first perfect square is 0. So to make this equal to 0, I'm going to have x equal 3. And then when I plug in 3 here, I get square root of 0, 0. 0 times -2 is 0, and then -2. And notice, it says to start at h comma k. Well, by doing this, we are starting by h comma k. So 3, -2, 3 is h, and then -2 is k. All right, well, I'm going to fill out the rest of my table, and then we'll graph. The next perfect square is 1. So to get this inside of the radical equal to 1, I need x to be equal to 4, because 4 minus 3 is 1. And the square root of 1 is 1, times -2 is -2, minus 2 is -4. And I notice I just wrote 1 here by accident. That should be a 4. Anyway, the next perfect square is 4. Well, to get from 4, I need to do 7 minus 3. So this x value is going to be 7. So I'll make this 7. And then 7 minus 3 is 4. Square root of 4 is 2. 2 times -2 is -4. -4 minus 2 is -6. And then my next perfect square after 4 is 9. And 12 minus 3 is 9. So my next x value is going to be 12. And then I have 12 minus 9. I have 12 minus 3, which is 9. Square root of 9 is 3. 3 times -2 is -6. -6 minus 2 is -8. And then the next perfect square after 9 is 16. But that's not going to fit on our graph, as we can see, because that would be 19. 19 minus 3 is 16, and so on. But my graph only goes up to 18. You could, I guess, plot it if you wanted to, but I'll just stop here. And notice, my a value is -2. And if I put all these perfect squares here, or the x values that make the inside of the square root a perfect square, then look at the pattern. I keep adding my a value, -2. And then plus my a value of -2 is -4. Plus -2 is -6. Plus -2 is -8, and so on. So you can kind of see that pattern going on there. Anyway, I'm going to plot these points. So 3, -2. It's right here. And then I have 4, -4. Then I have 7, -6. And then I have 12, -8. And we can kind of tell that the next value would be 19, -10. And on this graph, this is 18. And then if I looked over, 19, -10 would be right there. So I'm going to put it here, but you don't have to because it's technically off the graph. But anyway, now I'm going to draw a sketch of a curve through this function, through these points. Put my arrow there. So I've successfully described the transformations from the parent function, and then I've graphed it using my table, and now we're done with this one. Example 5. The model v of d equals the square root of 2gd represents the velocity v in meters per second of a free-falling object on the moon, where g is a constant 1.6 meters per second squared, and d is the distance in meters the object has fallen. The velocity of a free-falling object on Earth is shown in the graph. Compare the velocities by finding and interpreting their average rates of change over the interval of d equals 0 and d equals 10. Well, if you remember, average rate of change is basically just finding the slope of the line that goes through those 2 points. So the slope of the line is just the change in y over the change in x. And in this case, it's going to be v of 10 minus v of 0 over 10 minus 0. Okay, so I can do that for this function. And then does this function have a name? It doesn't look like it. So maybe I'll call this one, call this f of d for the graph. Anyway, if I look at v of 10 minus v of 0, I can plug this into my scientific calculator to help me make the calculation. So my function is the square root of 2gd. And remember, for the moon, this is the model for the moon. We know that the constant g is 1.6. So I'm going to call this 1.6. So times 1.6. And then d is our input. Okay, well, d, we're going to have be 10 at first. So I'll multiply this by 10. And then I'm just going to copy and paste this to make my life easier. And then minus d of 0. But when this is 0, this whole thing is just going to be 0. So, I mean, you could put that there. You don't have to. And then I'm just going to divide this by 10 minus 0. I'm looking back over here. I wrote 10. This should be a 0. I apologize. Anyway, back over here. I see the average rate of change here is about 0.565. I'm going to round this up to about 0.57. So this is about 0.57. And then we're dealing with velocity, so I'm going to do meters per second. And now I'm going to look at the graph, which I'm calling f. You can call it whatever you want. Well, my output at 10, if I look here, is just below 15. I'm going to call that maybe 14. So it's going to be 14 minus. And then at 0, it's just 0. So 14 minus 0 over. Well, this is still going to be just 10 minus 0. Once again, I apologize for putting 10 minus 10 up there. So it's going to be 14 minus 0 over 10 minus 0. I mean, you don't really need a calculator to figure out that this is going to be 1.4. Well, I'll say approximately because I guessed on where that 14 is. So approximately 1.4 meters per second is my velocity. So obviously on Earth, the gravity is going to be more extreme. It's going to be, you're going to be falling faster than if you were falling on the moon. And we just used our average rates of change to compare that with the square root function. And now we're done with this one. For example 6, the velocity v in meters per second of a tsunami can be modeled by the function v of x equals the square root of 9.8x, where x is the water depth in meters. Part A, use a graphing calculator to graph the function. At what depth does the velocity of the tsunami exceed 200 meters per second? Part B, what happens to the average rate of change of the velocity as the water depth increases? Well, let's go to our Desmos graphing calculator, and I'm going to plug in my equation. V of x equals the square root of 9.8x. Okay, so here is my function, and I'm going to zoom out a bit because I'm dealing with like hundreds of numbers. So if I go back over to the question, it's saying, at what depth does the velocity of the tsunami exceed 200 meters? Well, the velocity is the output. So what I can do is graph y equals 200 here and see, I'll move this over. So the interpretation of this is that the velocity of the tsunami gets over 200 at about 4,082, let's say. Let's round this. So for part A, I'll write that down. So the velocity exceeds 200 meters per second at around 4,082 meters. All right, so now we're done with part A. So for part B, what happens to the average rate of change of the velocity as the water depth increases? Well, I'm going to go back over to the graph. And if I look at the graph, notice that it's increasing faster at the beginning, and then as I increase my x value, it slows down. My increasing slows down. My slope, if I had a line that went from here to here, the slope would keep decreasing. Okay, so I can show you what I mean by that. So what I've done is I've turned off the 200, so that's the 200, I turned that off. And then I plotted these line segments, which are the average rate of change, on top of our graph. So if I turn off the graph of the square root function, these are my average rates of change. So I calculated that by doing my output of my second value minus my output of my input value, and then minus how much of this range are. I'm picking 1,000 as my input range. Anyway, notice at the beginning my slope is higher. Okay, this slope is more steep. And then as I increase my x value, my slope gets lower. So this right here is even less steep, this right here is a little bit less steep, and this right here is a little bit less steep. So as I increase my x value, my slope gets less steep. And that's what I want you guys to get out of this. So if I go over here, what happens to the average rate of change of the velocity as the water depth increases? The average rate of change decreases as x increases. So I finished both parts of this question, and now we're done.